In this video, we'll continue talking about forming enolate ions, but we'll consider both thermodynamics and kinetics. So for an asymmetrical ketone, there are multiple enolates that could form, and we'll see an example of that. And one may be the kinetic enolate, and the other would be thermodynamic. So the kinetic enolate would be the enolate ion that forms faster. And the thermodynamic would be the one that is more energetically stable. So these may not be the same thing if we have an asymmetrical ketone. So let's look at an example. We will have ketone 2 CH3 groups. I'm sorry, right now it shows 2 CH3 groups, but we'll make one a CH2. So we have one of the alpha carbons is more substituted than the other. So both of those are alpha carbons. So we have 2 alpha carbons. So 2 different enolate ions are possible. So if we look we'll first do the CH3 group. So we have 3 hydrogens here. These are all alpha hydrogens. And so if we remove one of them, of course we need a base to remove that alpha hydrogen. We saw these mechanisms in the previous video. If we have a base to remove the hydrogen, then we now have 2 here. So we've removed an alpha hydrogen. We've formed a pi bond, and we have a negative oxygen here. So again, the mechanism for this is in the previous video. Now, because there are 3 possible hydrogens at this alpha carbon, as opposed to 2 at the other alpha carbon, the first enolate ion that we've drawn is the kinetic enolate. This means, again, it forms faster. Now let's look at what the enolate ion would look like if we remove the other more substituted, a hydrogen from the other more substituted carbon, so the left of the molecule. So if we removed an alpha hydrogen from the alpha carbon on the left, then now we only have 1 hydrogen there. We have a carbon-to-carbon double bond, negative oxygen, and our CH3 group. So we still have these 3 hydrogens here. And in our first product that we drew, we still have those 2 purple hydrogens. So the second enolate ion that we drew with the carbon-to-carbon bond towards the left of the molecule, this is the thermodynamic enolate. This is more stable. So the difference between these 2 enolates is, of course, which hydrogen is removed in the location of the double bond. And so the first one, the kinetic enolate that we drew, is the kinetic enolate. It forms faster because there are 3 available hydrogens to be removed, as opposed to the thermodynamic enolate, we're removing a hydrogen in a spot where there are only 2 hydrogens. So our kinetic enolate forms faster, again, because we have 3. So any one of those 3 hydrogens could be removed to form the kinetic enolate. As opposed to forming the thermodynamic enolate, there's only 2 hydrogens. The thermodynamic enolate is more stable, and this goes back to Zaitsev's rule. This is something we covered in Organic Chemistry 1. And this is that more substituted alkenes are more thermodynamically stable. So in the thermodynamic enolate, our alkene is between these 2 carbons. One carbon is bonded to an oxygen and another carbon. The other, that's part of the double bond, is bonded to one hydrogen and a carbon, the R group. If we look at the kinetic enolate, one carbon that is part of the double bond is bonded to an oxygen and another carbon. The other is bonded to 2 hydrogens. So this kinetic enolate, although it forms faster, it's less thermodynamically stable. If we think about this on an energy chart, you might remember doing these reaction coordinate diagrams. Gibbs free energy on the y-axis, reaction progress on the x-axis. For both of these, we're starting with the same ketone, so our starting material is the same. To form the kinetic enolate, which I'll abbreviate with Ke, this forms faster, which means it has a lower activation energy than the thermodynamic enolate. But the thermodynamic enolate is a more energetically stable product, so that will exist at a lower energy than the kinetic enolate. So if the kinetic enolate requires this much activation energy, relatively, the thermodynamic enolate might require more, but we're producing a more stable product. So again, if you have an asymmetric ketone, 2 different enolates would be possible. The one that forms faster is the enolate that's formed from removing a hydrogen where there are more possible hydrogens to remove. So that's our kinetic enolate. And then our thermodynamic enolate is the enolate that is more stable, and that's formed by, or that forms a more substituted alkene. So generally, the thermodynamic enolate would be produced more in higher concentration because it is more stable. Reactions tend toward more stable molecules. But we can favor the formation of the kinetic enolate of a ketone by using a large base. So the kinetic enolate is favored when the base that's being added, so we add a base in both cases, when the base that's being added is a large, bulky base. And then the thermodynamic enolate is favored when using a smaller base. So you can control which enolate is formed based on which base is used for the formation of the enolate. Okay, so different bases will favor a different enolate. Again, if you have an asymmetric ketone. So let's look at two examples here. We'll use the same general asymmetric ketone to talk through what's going on here. So we have our 3 hydrogens in the CH3 group. And then 2 hydrogens at the CH2. These are all alpha hydrogens. Now, one common bulky base that's used is lithium diisopropyl amide. This is abbreviated as LDA. So this is a useful base to remember, both the abbreviation and the structure of this base. So let's draw out the structure. We have lithium diisopropyl amide. Well, we have lithium. Lithium has a +1 charge. We have diisopropyl amide. We have a nitrogen with 2 isopropyl groups. And then we have a positively charged lithium, so we must have a negatively charged nitrogen. So that nitrogen has 2 sets of lone pairs. So these now are bulky groups. The 2 isopropyl groups take up a lot of space around the nitrogen, so we call this a bulkier base. So this would favor, go back to earlier in the video, this would favor forming the kinetic enolate. So since the LDA is bulkier, it is easier for it to remove one of these 3 hydrogens at the end of the chain. We'll show the electrons going to the carbon. It's more difficult and less likely for the LDA to come and remove one of these hydrogens from the CH2 group because there's this R group blocking access to those hydrogens there. So the LDA will form the kinetic enolate. So we have 1 hydrogen removed from the CH3 group. Remember that the enolate can be shown with a negative charge on the carbon. And then just as a reminder, you can also show the negative charge being owned by the oxygen. So this is resonance here. The double bond. So both are structures of this enolate. So with a bulky base, the kinetic enolate is favored. Now let's look at a smaller base. So redrawing this asymmetric ketone, I'll emphasize all of the hydrogens again. All of the alpha hydrogens. A small base, one of the smallest bases, or maybe the smallest base, is sodium hydride. We've seen this base before. We have sodium with a +1 charge, and then hydride, hydrogen, with a pair of electrons and a -1 charge. Now, this hydride is very small. Hydrogen is the smallest atom. This is a very small base. And so it is easier for this small base to access the hydrogens that will produce the more thermodynamically stable product. So in the product, we've removed one of the alpha hydrogens, generate a negative charge on that carbon. We could do the same resonance as we did in the previous example. And we still have all three of the hydrogens from the CH3 group. So with a smaller base, the thermodynamic enolate is favored. Just to be consistent here, I'll draw the resonance structure. We resonate those electrons there. We can show the negative charge owned by the oxygen. We have a double bond here.